It's interesting that for the first time, we have enough people presenting to fill 2 rooms. We also have a representative from Lehigh University with the poster here. They have been very interested in our capstone model and have essentially replicated it in Japan. And so now the way that we have been doing the capstones has been sort of migrating around the world. The Seattle campus, the EE program there, has also started a capstone program that's very much like ours, which they call the entrepreneurial capstone. And I think schools are seeing the value of giving students projects that represent real world problems companies are interested in solving, as well as supporting faculty research in the case of 2 of the teams today, supporting the work that I do. So with that, I will let the first team start. And I should say this, as just an introduction, when I teach a class, one of the first things I do is when I give back homeworks for the first time, I actually try to hand them back to each student, people in my class, even know them. And I try to learn to pronounce the student's name when I do this. And I can see students cringing when I pronounce or mispronounce or garble their name terribly. So I'm going to save them the embarrassment this time and let them introduce themselves when they each team gives the talks. So the first talk is sponsored by Ventec, which is a small company here in Bothell. They've been very supportive of our program. Thank you for that. The project is an oxygen module test fixture. The mentor is Doug DeVries. Is Doug here? Okay. The faculty advisor is Dr. Eric Sotom. Thank you, Eric. And I'll turn it over to the team.
All right. Good afternoon, guys. Welcome to our capstone presentation. The last 2 quarters, we've been working on our oxygen module test fixture, which is, as Dr. Arnie Berger announced, was sponsored by Ventec Life Systems. I'm Carl. This is Victor. This is Bree, and this is Jen. So a little background on Ventec Life Systems. They were founded in 2012 by Douglas DeVry. For our capstone project, we were provided with a human resource, Daniel Trott. He's a mechanical engineer over there at Ventec Life Systems. What Ventec does is they develop and manufacture portable life support ventilators, which involve breathing support, cough assistant, suction, and nebulization. In April 2016, they expect to introduce their ventilation line, which includes 3 different types. There's going to be a VLS 1000, a VLS 1002, which is going to be used for home care and long-term care patients. The VLS 2000 is going to be used for patients in transport and long-term acute care environments. As of now, Ventec is currently manually processing their system, so testing the flow and leakage all manually. So what Ventec has asked for us to do is to design an automated testing process system. This system is used to speed up their testing process and help them meet their April deadline or any other deadlines that they have. Our system is used to read the flow going through this chassis that we made over here, our design, and the readings are going to be output onto the computer, which will then be reported to a printout onto the computer, which will then provide pass or fail whether each case that we were required to do occurred. When it's all said and done, Ventec does plan on using our testing system in their testing line. They've asked for us to check the forward leakage, the reverse leakage, and the flow through the solenoids inside our unit under test. The 2 solenoids are located right there, and the unit under test will be placed here on our board. So a little flow chart to basically explain what's going on. We have our pneumatic testing equipment, which include the soft start, the alley cat, the pressure and flow transducers, and the solenoids. Each component here is powered through the NI Compact DAC, which is coded through LabVIEW in a PC, Windows PC with LabVIEW software. What the Compact DAC does is it sends the signals to our components, which then provides readings back to our lab view and then outputs onto our display screen, determining whether or not that our system failed or passed. The 2D barcode scanner is used to scan the serial numbers on the UUT to determine which product is being tested at that time and to determine which testing system that they're using and which part is being tested in that certain system. For our design process, for the hardware, we researched each part on Google. We came across Omega, AliCAS, and the TSI. And once we reached those, we looked up which would give us the best results within an acceptable range. We then went back to Ventec, talked to Daniel, the ME over there. He recommended some parts for us to look up, which we did, and it helped out a lot. After that, we created our BOM, our bill of materials, with the amount of parts we would need, the part number, and the vendor information. From there, we created our bill of materials, brought it back to Ventec, and verified and finalized our materials. The software that we used were SolidWorks. SolidWorks was used for 3D modeling and designing and formatting our system, and LabVIEW was used for coding and getting the measure of the results. Microsoft Office was used for our papers and our presentation slides. We're going to hand it off over to Victor, who will talk to you guys about hardware.
The hardware portion of our test fixture, we can divide it up into three major categories. We have the compact DAC chassis system, the pneumatic control devices, and the pressure and flow measurement devices. So our first major system is the compact DAC chassis system. This system provides us a platform which we can customize via the various input-output module that allow us to either acquire or generate both analog or digital signals. It utilizes a single USB cable for communication with the software and accepts up to 4 different input-output modules. For our test fixture, we utilize 2 power supply modules, one analog input module and one analog output module. So for the 2 power supply modules we use, they are the National Instruments 9474 digital sourcing output modules. These modules are used to power on our 24-volt and 5-volt devices in our system. These modules provide an attractive solution to powering on pneumatic control equipment, and each of these modules requires an external power supply. And for our test fixture, we use both a 24-volt and 5-volt external power supply with each of these modules. Now, our second major category of our hardware is the pneumatic control devices. These devices are used to safely start and stop the system, control airflow direction, and pressure. In order for us to safely start the system to begin testing, or safely shut down the system in the case of an emergency, we utilize a soft start valve. This valve is manufactured by Exelon and is the P72 series. In order for us to have bidirectional airflow control, we chose to use 3-way solenoid valves, which are manufactured by GEM Sensors and Control. And in order for us to control the pressure for our various testing conditions, we used an electronically controlled pressure regulator. This regulator is manufactured by AliCAS, and it accepts between a 0 to 5-volt analog input signal in order for us to set the pressure. And as an additional safety measure, we included a manually operated ball valve at the input of our system. Our last major category is the pressure and flow measurement devices. So based on our required test conditions, we need to measure both flow and pressure. And due to our wide range of flow rates, we had to use 2 different flow transducers. One flow transducer is used for our high flow conditions, and it can be seen here this is the TSI one. And then we have our low flow condition one, which is manufactured by Omega, and this is yellow. And for all our pressure measurements, we use a single gauge pressure transducer. It is located here. And here we have our complete electrical schematic. We can kind of break this up into 4 major regions. In the upper half in blue, we have the 4 input and output modules. 2 of our power supply modules, 1 analog input module, and 1 analog output module. Then we have our external power supplies, which are in green. We have 2 power supplies, the 5-volt and 24-volt, which are used in conjunction with the power supply modules. Then in purple, we have the pressure and flow measurement devices. We have our 2 flow meters and our single gauge pressure transducer. And finally in red, we have our solenoids, 4 of our 3-way solenoids and our single soft start valve. And here we have our complete pneumatic flow for our system. This shows the flow through our system for our various test conditions, both our reverse, our forward, and our 2 flow through tests. At the beginning of our system, we have our pressure regulation stage. This controls the pressure and sets it for our various testing conditions. Then we have the airflow directional stage, where we control the airflow to test the various components of the unit under test. And finally, we have the flow measurement stage, where we get our flow measurements and determine whether or not the unit under test has passed or not. And next, we have Bree, and she will be talking about the software portion of our testers.
So as mentioned before, we use SolidWorks and LabVIEW. SolidWorks is a 3D modeling system, and this included the entire chassis. So we included the compact DAC in each of the 4 modules, as well as every nut and bolt. With LabVIEW, we control the entire system. And LabVIEW is a system design platform for visual programming language. So beginning with our software flowchart, we have a start button that will apply 24 volts to the soft start, alley-cat, pressure transducers, and flow transducers. And then there's a 5-minute warm-up so that the flow transducers are able to take correct measurements when we need them. So for case 1, the forward leakage, we begin by taking the pressure measurement and checking to see if it's within the range of 87.5 psig to 88.5 psig. And if it is not, then we will increment or decrement depending on where it's at, and the alley cat will increase or decrease as well. Once it is within range, we'll take the low pressure flow measurement and write that to the document, as well as compare it to if it is less than 0.01 liters per minute. That is also written to the document. If it passes, it will be written as pass. If it fails, fails. For case 2, the reverse leakage, the process is very similar except for the movement of the air. We have to turn on solenoids 2, 3, and 4 so that we're able to measure the air through port in front of port B. We once again take the pressure measurement and check to see if the pressure is within 11.5 and 12.5 psig and change it accordingly. We'll take the low pressure flow measurement as well and write that to the document, and also do another comparison similar to case 1. it must be less than 0.01 liters per minute. For cases 3 and 4, this is for the flow through each of the solenoids. They have the exact same setup where the first solenoid is turned on and the other ones are turned off. In case 3, the first solenoid inside the actual UT is turned on, where in case 4, the second solenoid is turned on. In this case, we want to make sure that there is a pressure of between 40.5 and 41.5 psig. And once it is within that range, we'll take the high pressure flow measurement and write that to the document, as well as compare it to be greater than 45 liters per minute. And finally, we compare all of the 4 cases. If all of the cases pass, then the UT passes. If only one fails, then it fails. And this is also written to the document and finally ends by printing the results. Next, we'll have journaling with the testing, verification, the lessons learned, and conclusion.
So for testing and verifying that our system was working correctly, we first tested each component individually. We would test the solenoids, the pressure transducer, the flow transducers, etc. After that, we would test the individual systems. So we would connect the pressure transducer, flow transducer to the DAC. Once we saw that there was communication, we tested the system as a whole. So for example, we would test, to make sure that the system was working correctly, we would have the air volume going into the system, and it should equal the air volume coming out. And the requirements that Ventec wanted us to meet were the forward leakage, the reverse leakage, the flow through SB9, and the flow through SB10. And for example, in case 3, we had our flow through SB9, and we would be applying 41 psig to the input port, and we would be measuring a flow greater than 45 liters per minute. Specifically, when testing each component, we would be applying voltages to the solenoids, the soft start, the alley cat, and also the compact DAC. To make sure that they were working, we would hear a clicking sound with the solenoids and the soft start. And to make sure that the alley cat was working, we would see a display on the screen. For the pressure transducer and the flow transducer, we didn't verify them ourselves, but we had verification and certification from the manufacturers that they were working. And again, we did verify that there was communication by connecting all the components that we had to the compact DAC. Here we have an example of the UT that we were given from Ventec, and each ventilator that Ventec produces has a UT inside. And we are connecting the UT to our device right here, and it makes sure that there's no leakage, the pressure is accurate. Here we have the results that we got when testing the UT. For our forward leakage case, we were to measure flow into port A being less than 0.01 liters per minute. And on average, we got 0.00208 liters per minute. For our second case, we had the reverse leakage. We're measuring flow into port B being less than 0.01 liters per minute, and we got 0.000182 liters per minute. For case 3, we had the flow through SB9, and the flow coming out of port B should be greater than 45 liters per minute, and we got 48.134 liters per minute. And lastly, flow through SB10, the flow out should also be greater than 45 liters per minute, and we got 46.642 liters per minute. And we can see that all of our cases did pass. Lessons we learned when finishing our capstone is we developed new skills working as a team and also with an up-and-coming company. Problem solving and debugging for larger projects did take extra time. And if we did have extra time with our capstone, we would like to put the oxygen module test fixture into an enclosed box, make it accessible. We would like to add an air filter to the beginning of our system, but at Ventec it wasn't required because they have a filter in their environment. And also we would like to change plastic barb tube fittings with brass fittings to ensure that there wasn't any extra leakage. And in conclusion, we did complete the oxygen module test fixture, and it automatically runs through our 4 test cases. We met all of Ventec's requirements and deliverables, and we enjoyed working with them. Thank you, and are there any questions?
Yeah, good.
What's a UUT?
This is a unit under test,
Oh, okay.
which was that external oxygen controller with the long strands of wires.
Okay.
So each ventilator will have a unit under test, in each of the ventilators.
Okay. And then, what does the G mean on TSIG?
Pounds per square inch gauge.
Gauge? Oh,
Yeah.
okay.
Did you ever test a failure?
We did. We just needed to unscrew the solenoids and leave it under test. And so once we did that, it would fail.
So I was curious, if everything passed, you never know.
Yeah.
The
Yeah, we had failures.
UTs that they gave us all passed, so they wanted to make sure that it did, and they told us to get, if we wanted to fail, just to unscrew the ball a little bit, so that the solenoid
There would be
fully.
leakage, yeah.
Yeah.
So are they gonna use this?
Yes.
Randy, you have a question?
Yeah, just curious, for any test measurement system, you have to understand gauge and R, which is repeatability, reproducibility. So do you actually look into that, or?
Not too much, we didn't really look into that too much. Most of our, either flow or pressure transducers have a pretty high repeatability to them. Their rating was greater than what Ventec looked at, but we didn't really look at, running a lot of tests with different units and getting kind of like, seeing if it really repeats.
Is that something they plan to do?
Probably, yeah. But
What was your biggest troubleshooting experience with it?
I'd say that after just all the wiring, because there's a lot of wires for each individual component. And when we put it all together, sometimes if we were moving one thing, we would accidentally unplug another thing, and it'd take a few days to figure that out.
I think also coding in LabVIEW and making 3D models in SolidWorks, it was a first for a lot of us. So learning it also and designing in it we learned a lot.
One of the things we looked at your project for, would be a capstone project that had a mechanical engineering student on it as well. Would that have helped you?
Definitely.
I think
Yeah,
it
definitely
definitely,
for that.
I felt like I was a mechanical engineer.
Any other questions? If not, thank you.